Hi, so in this video, I want to revisit the mod 9 up counter that we did in a previous video. But if you recall, that mod 9 up counter was asynchronous, and it used this method that we called Asynchronous Reset to reset the counter. So what we did to make a mod 9 up counter, and here, let's go find it, is we built actually a mod 16 ripple up counter. So remember, this was the asynchronous method. And then we added this NAND gate over here, and the function of this NAND gate was to asynchronously reset all the flip-flops as soon as we reach the first invalid state, which in the case of a mod 9 counter would be 9. Now, there were actually two problems that we had with asynchronous counters that we can see in the timing diagram. So the first and most glaringly obvious problem is that we have this weird glitch over here in Q0, and that glitch is caused by the fact that when Q3 and Q0 are both high, so when that condition is detected, and this only occurs for the first time when the counter reaches 1001, which is 9, the NAND gate, whose inputs are Q0 and Q3, goes momentarily low. And when that happens, because the output of the NAND gate is connected to the asynchronous reset of all the flip-flops are reset back to 0. The condition for the NAND gate to be low is no longer there, and the NAND gate goes high again. So the effect in the mod 9 counter is that we have this weird glitch where Q0 goes momentarily high. It's detected by the NAND gate goes low, resets all the flip-flops, and then all the flip-flops are reset back to 0, all the Q outputs. So that's one thing that is a little troubling. We get this really ugly glitch. We don't really necessarily want it. And the second problem, so just to clarify, that problem, this glitch over here, this is caused by the asynchronous reset. And the problem that we have with asynchronous counters in general, so regardless of whether it's a natural mod number, that is a 2 to the n, or a non-natural mod number, so any other number other than like 2, 4, 16, etc., is that we have this issue where because the output of 1 is connected to the clock of the next flip-flop. So we get this sort of staggered delay that we can see over here. So looking at the timing diagram again, we can see that when the clock has a negative edge, some short time after that, maybe like depending on the flip-flop, but in the order of nanoseconds, and like usually not over double digits, the Q0 goes high. And again, here at the next falling clock edge, some very short time after that, Q0 will toggle again. And because Q0 is the clock for Q1, at the falling edge of Q0, again, we have that problem that after some slight delay, Q1 will go high. We see it again over here. It doesn't happen instantaneously. And it turns out this delay is just given by the propagation delay of the flip-flop. So looking at Q2, we see the same thing at the falling edge of Q1, some short time later, given by the propagation delay of the flip-flop. Now, this is a characteristic of the particular flip-flop that you're using and the logic family that you're using. So here we see some short time later, it does not happen instantaneously, Q2 will go high, and we have the same thing over here because Q2 is the clock for the flip-flop whose output is Q3. So this sort of cascading propagation delay, which leads to a cumulative propagation delay between Q3 and the falling edge of the clock, it's given by the number of flip-flops times the propagation delay of each flip-flop. This is a characteristic of all asynchronous counters, or ripple counters as we call them. So these are two problems that we have. We have the problem that we have this cumulative propagation delay, and we have this glitch over here caused by the asynchronous reset. So both these problems can be solved if we use a fully synchronous mod 9 counter. And I'm going to show you how to do that, because previous to this, in the last video, we only did natural number mod counters. But now let's see how to do it with a non-natural number, at least synchronously. So, and we will revisit this after, because there are a few other things that I would like to point out to you. So of course, the first thing that I want to do when I build any kind of state machine, of which a counter is a type of state machine, is I want to draw the state transition diagram. And in this case, because it is a mod 9 up counter, what I want it to do is to count from 0 all the way up to 8. So recall that in a state transition diagram, all the states are in these little bubbles, and the transitions are indicated by these arrows. But these transitions are, first of all, they're unconditional. They happen regardless. And second of all, I would like to point out that these are synchronous transitions. They occur at the edge of the clock. So over here at state 8, I am going to go directly back to 0. Now, what about all these remaining states over here? So these are the sort of invalid states for a mod 9 up counter. Well, let's revisit them. Here, the excitation table for our mod 9 up counter. Okay, so where do we start? In an excitation table, we always start with the present state. Now, I know that I'm going to need 4 flip-flops. How do I know that? Because to represent mod 9, counting from 0 to 8, I need 4 bits to represent 8. So I am going to need 4 flip-flops. I need 1 flip-flop per bit. So let's call them Q3, Q2, Q1, Q0. And then I have next state over here. And the next state, I also have Q3, Q2, Q1, Q0, but because they're the next state, I'm going to indicate that with this superscript, this plus sign. And now when I do control inputs, so this is dependent on the type of flip-flop I use. Now, D flip-flops are fairly straightforward. So for this example, I'll use JK flip-flops. So how many JK control inputs do I need? Well, I need 1 J and 1 K per flip-flop. I have 4 flip-flops, so therefore I have 8 control inputs. I have J3, K3, J2, K2, J1, K1, and J0, K0. And now I'm ready to make my excitation table. So where do I start? So let's start by filling it out. So I started off like a truth table. So I am just sequentially listing all the possible 16 permutations of Q3, Q2, Q1, Q0, and increment by 1 each time. Now, if I do it this way, it just makes it a lot easier for me to do my key maps later. So how do I know what to write for the next state? I mean, that's really simple. I just need to look over here at my state transition diagram. So in a mod 9 up counter, and again, I can read this directly off the state transition diagram. In a mod 9 up counter, if the present state is 0, at the next clock transition, I want the next state to be 1. I'm counting up. And if the state is 1, the next state will be 2, and so on. And I just continue like this until I get to state 8. At state 8, I reset the counter, so the next state after that is just going to be 0. Now, I'm getting to the invalid states, and as the designer, I have a decision to make here. So I can choose one of 2 options. I can say you know what, it doesn't matter what the next state is. And then I can put X's in all the rows and columns here for the next state. Or I can say, you know what, it's really important for me that should I power on my flip-flops or power on my counter and I find myself in one of these invalid states, that I know precisely what the next state is going to be. Maybe I want the next state to always be 0. So as the designer, you have two options here. Now, if you specify a particular next state, then you will have much more complicated Boolean logic expressions in the end for all the control inputs. So I'm going to take a gamble and I'm going to say, you know what, I don't care what the next state is going to be. I'm just going to put a whole lot of X's here for the next state. Now, this is a gamble, and it could pay off like all gambles. It could have, it's high risk, high reward, right? So it can pay off in that I will have greatly simplified logic expressions, but I'm taking a risk because what if I power on my counter and I find myself in one of these invalid states and somehow the next state resolves to another invalid state and I never make my way back into the counting sequence. It just kind of bounce around between invalid states for all of eternity. So of course I don't want that to happen. So I'm going to have an extra step. If I decide that my next state for all my invalid states, my next state is going to be don't care, then I am going to have to go back and revisit that decision and see if actually my next state leads me somehow into a valid counting sequence. And I'm going to show you what that's like a little bit later. So to do the control inputs now, and you should know this from previous videos, so I'm not going to go over the derivation of a single JK flip-flop excitation table, but I mean, it's worth it to write it out. I always write it out. So single JK flip-flop excitation table. So for a single JK flip-flop excitation, I'm going to write what my present state is. That's Q. My next state, that's Q plus, because again, this is for a single JK flip-flop. My control inputs are J and K. And what does it look like? It looks like this. So these are all the possibilities for present and next state. And my JKs look like this. And if you're curious how I got this, it is in a previous video, so go check it out. Now I come back up here, and my strategy again, as always, is to look at the present state and the next state, and then figure out what J3 and K3 have to be. So I do it flip-flop by flip-flop. So I'm just looking at Q3 now. For the 0 to 0 transition, I know that I need to have J and K equal to 0 and X. And again, over here, I have a 0, 0 transition. So that's 0X. Again, 0, 0. So that's 0X again, and 0X again, and 0X for quite some time. And now, finally, I have a 0, 1 transition over here. And if I go back to look at my single JK flip-flop excitation, that corresponds to this row. So I know that if I want a 0 to 1 transition, then J and K have to be 1 and don't care for K. And I've got over here a 1 to 0 transition in the next row. So that's when it's the counter is resetting from 8 back to 0. For a 1 to 0 transition, I have X1. And what do I do over here? Well, I just said I actually don't care what my next state is. So that was a decision that I, as a designer, took. So that makes it a lot easier. Everything from here on in becomes a don't care. Okay, how about J2 and K2? So in order to fill these out, I need to be looking at Q2 present state and Q2 next state. And over here again, I have 0, 0. So J2 and K2 have to be 0 and don't care. Then another 0, 0. So that's another 0x. Another 0, 0. So that's 0x. And here I have a 0, 1 transition. For a 0, 1 transition, we said it's 1x. Next, what I have to do is a 1, 1 transition, and I've got a couple of those. So 1, 1, I need x0 for jk. So that's x0, another 1, 1, x0, another 1, 1, x0, and then over here in this row, I have a 1 to 0 transition. We said 1 to 0 transition is x1. x1 goes over here. And what about the next row is just a 0 to 0, which we said is 0x. There we go. And for all the rest, because my next states are don't care, so I don't care what the control inputs are. So I'm just going to put x's all the way down. All right. And back to J1, K1. So I'm trying to do these control inputs over here. And to do that, I need to look at Q1 present state, Q1 next state. So we'll go row by row. 0, 0. So that gives me a 0x. Now I have Q1. I'm looking at Q1, present state, next state. I have a 0, 1 transition. So for 0, 1, that's 1x. How about next row? Next row I have 1, 1. Well, 1, 1, according to this, is x0. And I'm going to just fill it all in, but it's a good exercise for you at home to try to do it yourselves and see if you come up with the same answer that I do. So what you should have ended up with is the following excitation table. So I filled out the control inputs J3 and K3 all the way to J0 and K0. And now I will do the K-maps with you because some of you have asked me for a little bit of extra time to do the K-maps. So let's go ahead and do that. So I start with Q3 and Q2 are my inputs, and Q1 and Q0 up here. And just going to get my K-map set up with the gray code. Here we go. Okay, so let's start with J3. So recall that we need 8 Boolean expressions, 1 for each control input, right? And we have 2 control inputs per flip-flop. So that is going to lead us to 8 Boolean expressions, 1 for each control input. So let's start with J3. So what I do is I'm looking at this column over here, and I'm going to fill in the K-map. So I'm going to start with 0, 0, 0, 0, 0, 0, 0, 1. And the rest are all x's. X, 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 X. And I see by looking at the K-map that I can circle these two over here. And that gives me an expression for J3 that is Q2, Q1, Q0. And now we're going to do K2, and I'm going to reuse the same K-map. So I am looking now at this column over here, K3. So I'm looking at this column over here for K3, and I'm going to fill in the K-map as X, 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 again, X, 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 X. So that brings me to here. And now I've got 1 X, 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 and X, 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 X. A lot of don't cares. So how can I simplify this? Well, that's pretty simple. I just say that K3 is equal to 1. How about J2? So we're looking over here at this column, and I'm going to fill it in. So 0, 0, 0, 1, X, 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 0, X, 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 and X, 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 X. The rest are don't cares. So how can I simplify? I can simplify this column over here. And that gives me J2 equal to Q1, Q0. How about K2? So again, I'm going to reuse the same K-map. You could just skip this part if you're comfortable with K-maps or you're using some other method to generate your Boolean expressions. K2 over here, but if you need a little refresher, stick with me. So K2, what do we have? X, 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 and then 0, 0, 0, 1, and then X, 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 and X, 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 X. So what do we have? Again, we have this column right here, and we can say that K2 is just equal to Q1 and Q0. Next, we've got J1 followed by K1. I'm going to erase the K-map, and I'm doing J1 now, which is this column over here. So I've got 0, 1, X, X, 0, 1, X, X, and 0, X, 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 and then just a whole bunch of don't cares. So how can I simplify this? I can select basically this grouping over here would be the simplest, and that gives me an expression for J1 that is simply Q0. All right, I'm gonna again reuse my K-map for K1. So for K1, using this column right over here, and I've got X, X, 0, 1, again, X, X, 0, 1, and the rest are don't cares. So what can I do? Again, I've got this same grouping over here, and that gives me K1 equal to Q0, and I can see at a glance, I'm not going to do the K-maps for these because I can see right away J0 and K0. If you look at the corresponding columns, I can see that the values for J0 and K0 are either 1 or don't care. So in that case, it makes my expression pretty simplified. I can say that they're both high. So what does this look like as a schematic? So what we're going to do is create a new page over here where we can draw the schematic. So again, this is a synchronous mod 9 up counter, and it's fully synchronous. And I'm going to draw the schematic just to show you. But let's bring our Boolean expressions in. So I need 4 flip-flops. Why 4 flip-flops? I need 1 per bit. And what I'll do is I'm going to say that the leftmost flip-flop corresponds to Q3 and the rightmost corresponds to Q0. And now I'm not going to show R bar or S bar. Sometimes they're also known as pre and clear. They're usually active low asynchronous inputs. And for a fully synchronous counter, they've got to be high. Or alternately, you could call it pre or clear. So it really depends on the type of flip-flop that you have and the logic family. So in other words, my asynchronous active low inputs need to be inactive for a fully synchronous counter. So for an active low input to be inactive, that means it has to be logic high. So I'm not going to draw it. What I'm going to do now is I'm going to put the clock, and the clock goes to the clock input of each flip-flop. And you know what, for fun, let's leave them positive edge triggered because I want to show you that actually does not make a difference. In a synchronous counter, the edge triggering of the clock is irrelevant. Now, the other thing is that in a fully synchronous counter, so we said that this corresponds to Q3. And I'll show Q3 bar, but the counter outputs always come from Q. So if you'll recall when we were doing asynchronous counters or ripple counters, we said that you could either take the Q or the Q bar outputs as the counter outputs. But in a synchronous counter, because if you look at the excitation table over here, I've actually kind of implicitly said that the present state is determined by the Q outputs, not the Q bar outputs. So let's continue. I have J2, K2, Q2, Q2 bar. J1, K1, Q1, Q1 bar. Okay, and now how do we implement this expression? Well, we said J3 is simply equal to Q2 and Q1 and Q0. So what I'll do is I'll just make a 3 input AND gate. However, I want you to note that this 3 input AND gate consisting of Q2, Q1, and Q0, and the output goes straight to J3. I could also have drawn it, and in fact, let's do it. Why not? I could also have drawn it, if you only have 2 input AND gates handy, I could also draw it this way. This is Q2 and Q1. And then I have a second cascaded AND gate. And this goes to J3. And how about K3? Well, K3 goes to VCC. It's logic high. Now, J2 is simply the same as K2, and they are both equivalent to Q1 and Q0. How about J1 and K1? Well, these are both equal. J1 and K1 are equivalent, and they are both equal to Q0. So we'll just draw a wire directly from Q0 to J1 and K1, and J0 and K0 are always high. Okay, so that's our schematic. However, there is one additional step that we need to take. Now, as you recall, when we did the state transition diagram, we kind of left it up in the air what we were going to do with all these invalid states. And we said, you know what, we don't care what the next state is going to be because I want to simplify my logic expressions. But like we've been saying this whole time, when you power on a flip-flop, you don't know, it's not deterministic. And if you have not specified it by one of the inputs, you actually don't know what state a flip-flop is going to power on into. So what we need to do is we need to validate. So what I'd like to do is validate the next states given what I know the Boolean logic expressions to be. So here are my Boolean logic expressions. What I'm going to do is a kind of reverse excitation table where I know the present state. Let's draw it down here. So I know the present state. Let me label clearly what we're doing here. We're validating the invalid next states. Now you only need to do this if you're using don't care conditions for the next states. And in the next example, I'll show you what happens if we specify what the next states are going to be for each of those invalid states. So we have present state, and in an excitation table, this is where we would have the next state. But here, I'm going to write what the control inputs are. And over here, we're going to figure out what the next state is going to be. So in an excitation table, I know the present state and I know the next state. And the job of an excitation table is to determine the control inputs that take me from one to the other. What I'm doing here is subtly different. What I'm doing here is I've got a present state. Now I'm only doing this for my invalid states, which are these. So what I'm doing here is for each of these invalid states, in other words, anywhere from 9 all the way to 15, I am going to figure out what the control inputs are based on these Boolean expressions. And then I'm going to determine based on that what the next state is. So let's see how that looks. So my present states, I have Q3, Q2, Q1, Q0. My control inputs, I have 8 of them. And here are my next states, which are Q3, Q2, Q1, Q0, plus. So I denote next states always with a little subscript. Okay, so in this present state column over here, I'm only going to write these invalid next states, invalid present states, sorry. So let's write them. So they're everywhere from 9, 10, 11, 12, 13, 14, and 15. These are all my invalid states. So I'll just Note that. So I only have to do this for my invalid states when I'm using don't care conditions for the next state. So I'm trying to figure out, I mean, I said I didn't care, but in actual fact, I do care. I want to make sure that I have a valid path. If I power on in any of these invalid states, am I eventually going to end up in the valid counting sequence? So if you look at the state transition diagram, once I'm in here, I'm fine. If I'm in any one of these states, it's fine. I will just continue to loop from one state to the next for all of eternity. But I want to make sure that if I power on my counter and I find myself in any one of these states, that I have some way to get back into the valid counting sequence. So that's what I'm trying to do here. So how do I do this? Well, I'm going to look at the Boolean expression. So I'm going to start with J3. So J3 is equal to Q2 and Q1 and Q0. Therefore, it's only high when Q2, Q1, and Q0 are all high. And that only occurs here. So J3 is only going to be high in this state, and in all the other cases, it's going to be low. What about K3? So K3 is just high all the time. Okay, looking at K2 now. So K2 is high whenever Q1 and Q0 are both high, right? So that only occurs here and here. So K2 is high in this condition. I believe I skipped J2, but actually J2 and K2 are identical. So they're both only high here and here. And in all other cases, they're going to be 0. All right. What about J1 and K1? Well, they're just equal to Q0. And Q0 toggles at every point in the sequence. So J1 and K1 are going to equal 1, 0, 1, 0, 1, 0, 1. Same for K1. It just follows Q0. J1 and K1 are both equal to Q0. How about J0 and K0? That's pretty easy. They're just high all the time. In other words, they're in toggle mode. Okay, so with this information, we are going to determine, so remember, we're going to look flip-flop by flip-flop, and we know what a JK flip-flop truth table looks like. So if I know the present state, and I know what the control inputs are for each flip-flop, that lets me determine what the next state is going to be. So I'm going to do this flip-flop by flip-flop. So for Q3, the present state is always high. And I see that in most cases, J3 and K3 are in the reset condition. So the reset condition is when J3 is low and K3 is high. So here, let's write that down. Maybe people need a refresher. So let's put the JK truth table. And we have JK and Q. And I have 4 different combinations of J and K. So this is the hold condition. This is the reset. In other words, Q is going to be 0. This is the set condition. Q will be 1. And this is the toggle condition. So another way of saying that is that the next Q is going to be whatever the previous Q was in the hold condition. And in the toggle condition, the next state is going to be the opposite of what the previous state was. In other words, Q bar. So coming back over here for Q3 plus, I see that, let's look at just column by column and row by row. So Q3 is high and I'm in the reset condition. And in fact, actually, it doesn't matter what Q3 is, present state, because I'm in the reset condition this whole all the way down up until here. So in the reset condition, the next state Q3 is going to be 0. So for all these rows, it's going to be 0. And then over here, I'm in the toggle condition. So I see that over here, Q3 is high. I'm in the toggle condition. So next state Q3 is going to be low. It's going to be the opposite of whatever it was before. Okay, so far so good. What about Q2? So now I'm looking over here and I'm looking at the control inputs, J2 and K2. So I see over here that Q2 is 0 and J2 and K2 are in the hold condition. So what does that mean? It means that the next state Q2 is going to be whatever the present state is, which is 0. And same goes over here. J2, K2 also in the hold condition. Well, present state is 0. Next state is going to be the same thing, also going to be 0. How about over here? I'm looking at the wrong column. So J2 and K2 are in the toggle condition, and I have a 0, so I have to toggle the 0. The next state is going to be the opposite. It's going to be high. What about over here? J2 and K2. Again, I'm in the hold condition. I've got a 1, meaning the next state is also going to be a 1 because I'm in the hold condition. How about over here? I'm in the hold condition and I've got a 1. I'm going to hold that 1. Next state is also going to be 1. How about over here? Again, hold, again, 1. That gives me another 1. How about over here? I'm in the toggle condition, right? 1, 1 is the toggle condition. I've got a 1. I'm going to have a 0. Okay, so now I'm going to do the same, but for next state Q1. So I'm looking at present state Q1, and I'm looking at J1 and K1. So these columns over here. So let's see what's going on in this row. J1 and K1, I'm in the toggle condition over here. Q1 is 0, so the next state is going to be 1. How about over here? I'm in the hold condition. I've got a 1. Next state, also going to be 1. How about over here? Toggle condition. So I'm actually here, I'm sort of switching between toggle, hold, toggle, hold, toggle, hold, toggle. So over here, toggle condition, Q1 is high. I'm going to toggle that to a 0. Over here, hold, Q1 is 0. I'm going to hold that 0. What about over here? I'm back to toggle. I've got a 0. That's going to give me a 1. Over here, I'm in the hold condition. I've got a 1. I'm going to hold that 1. What about over here? I'm in the toggle condition. I've got a 1. I'm going to toggle that 1 to a 0. Okay, so what's left? Just Q0. I look at J0 and K0, and I'm going to determine next state Q0. So in this case over here, I'm in the toggle condition, and Q0 is 1. I toggle that 1 to a 0. How about over here? Again, toggle. And actually, I could just look down. I can see I'm in toggle all the way down. So whatever Q0 is, it's going to be the opposite at every stage. So if I had a 1, I'm going to have a 0. If I had a 0, I'm going to have a 1. So let's fill that in. That's it. So what do I do with this information? Well, I can see that when the present state is 9, the next state is going to be 2, 0, 0, 1, 0. So let's draw an arrow over here. Let's update our state transition diagram. So I know that in state 9, my next state is going to be 0, 0, 1, 0. All right, what about when my state is 10? So when I'm in state 10, the next state is simply going to be 3. All right, easy enough. You can see how this starts to get messy. So I'll draw it like this. And when I have a 3, now I'm going to look at the next state, 1, 0, 1, 1. So state 11. If when I'm in state 11, what's the next state going to be? 4. All right, let's draw that. Gets a little messy, a lot of crisscrossy lines here. Now, what about state 12? So look at state 12. What's the next state going to be? State 12, my next state is going to be 5. Can kind of see a pattern here. So state 12, next state is 5. I'm sure there's a neater way of drawing this. Okay, let's continue going. So where am I? 13. And the next state is going to be 6. It's getting kind of predictable. So let's draw another arrow over here. And what about this state over here? 14. When I'm in state 14, I can see that my next state is going to be 7. So let's draw another arrow. And now I just have to look at state 15. That's my last state. When I'm in state 15, next state is going to be 0. Finally, one that's less messy to draw. So here you have it. Now, what am I looking for here? I'm looking to see that if I happen to power on the counter in any one of these invalid states over here, that I will end up at some point back in the valid counting sequence, which is somewhere in here. Because once I'm in here, I'm stuck and I can't get out. And in fact, I do see that that is what happens. If I power on the counter in state 9, I end up over here in state 2, in state 10. If I power on in state 10, my next state is going to be 3, and so forth. So I can see that at every step, if I power on one of these invalid states, I do somehow end up back in the valid counting sequence. And that it actually happens for each of these cases, it happens at the next clock transition, which is fine. So even if it took me a couple of clock transitions, I just want to be sure that I will eventually get there. So that works. So in fact, this was a valid design, and I can continue with my schematic. Now, what do I want to say about this? So I want to note 2 things. So this is important. Let's write it down. Okay, so let's compare these a little. So we already talked at the beginning of the video a little bit about the shortcomings of an asynchronous counter. And we said that, first of all, I was sort of limited as to the maximum frequency I could operate it at, simply because I had this cumulative propagation delay given by, as you will recall, the cumulative propagation delay was given by the total number of flip-flops times the propagation delay of a single flip-flop. Therefore, I was limited. I cannot run it such that the clock frequency is less than this quantity over here, which means that the maximum frequency I could operate it at is equal to this, roughly. Okay, now, the second problem I saw was those weird timing glitches in the timing diagram, and those were caused by the asynchronous reset. So I only see those glitches when I have an asynchronous reset, which occurs when I have a non-natural mod number. So recall that a non-natural mod number is a mod number that is not equal to 2 to the n. So it's not 4 or 16 or 32 or what have you. So, I would only have these glitches during, and they're caused by the asynchronous reset. I would only asynchronously reset when I have a non-natural mod number, such as 9, which is the example that we did. But that is not the case here. I do not have these glitches. My timing diagram, in fact, is going to look, it's going to look great. I will show you what it looks like. So let's look at the clock. And we'll do how many of these? 1, 2, 3, 4, 5, 6, 7, 8, 9, and we'll just add another one at the end. Okay, and let's look at Q0, Q1, Q2, and Q3. And the first thing to note is that while in a ripple counter, Q1 is, well, so of course Q0 is staggered from the clock, but it's delayed from the edge by a small amount. Now, because I used positive edge triggered flip-flops in my schematic, I'll be consistent in my timing diagram. We'll just do these for a couple. So I'll note that now I'm arbitrarily going to say that I'm going to start looking at my timing diagram, and Q0, Q1, and Q2 are all going to be low. Now remember that they're all clocked by the same signal, which is this signal over here. So at some point, TPD, that's the propagation delay of a single flip-flop, after the positive edge of the clock, they're all going to change. So in actual fact, these guys are going to stay 0, but Q0 is going to go high. And then at some point later, it'll go low over here. It'll go high again. Q1 is going to stay low until here, and then it's going to toggle. And this is also going to stay low. And this is also going to stay low. Now, how do I know this? Because over here, if I look at Q3 as the most significant bit over here, this is Q2, this is Q1, and this is Q0, well, they're all low. In other words, they're all logic 0. Over here, I have a 0, 0, 1. 0, 0, 0, 1, I should say. And I know I'm counting up. It's mod 9. So what do I have here? 0, 0, 1, 0, 0, 0, 1, 1. In other words, these guys stay 0. This stays high. They both toggle over here. And notice, what I want you to notice here is that they're toggling at the same time. So we did not see this in a ripple counter. Now this is a telltale sign that what I'm looking at here is a synchronous counter. So I can see, I'm going to keep this low over here, because what I've got here is 0, 1, 0, 0. So Q2 goes high over here. It's going to stay high for a while. This stays low. So let's continue that. But what I see is that these are all toggling at the same time. And that time is some short time TPD after the rising edge of the clock. And let's make that explicit here so I can see. Now, when I see all counter outputs toggling, or when I see the counter outputs that are toggling toggle at the same time, then that is a clear indication that what I'm looking at is a synchronous counter. So I'll continue doing this. So I've mercifully filled this out for you. And what I can see looking at it is, first of all, two features should stand out to you here, which is, like I said, that when the counter outputs toggle, and over here at this transition between 7 and 8, they're actually all counter outputs are toggling. And I can see that they're all toggling at the same time, or at least you should see that. Maybe my drawing is a little bit messy, but I can see that at the rising edge of the clock, there's some slight delay. And again, that's given by TPD. But crucially here, it's the propagation delay of a single flip-flop. So I would not have this in a ripple counter. In a ripple counter, I would have Q0 toggling at some time TPD after the clock. But then Q1 would toggle at some time TPD after Q0, because remember, in a ripple counter, Q0 is the clock for the flip-flop whose output is Q1. And then I would have Q2 would toggle only sometime TPD after Q1 was toggling, and Q3 would toggle sometime TPD after Q2 was toggling. In other words, Q3 would be toggling at 4 times TPD after the rising edge of the clock. The other thing is that what I would see in a Mod 9 counter is, if you recall, I had that weird glitch where over here, Q0 would toggle as usual, and then it would sort of momentarily be high enough to activate that NAND gate, and then it would go back to 0. So I would have this little voltage spike over here. And I don't have that in a synchronous counter, a fully synchronous counter, which is what I have here. So these are the two features that let me know. So two features just by looking at the timing diagram or by looking at your waveforms on your scope. Those are two features that tell me right away that what I'm looking at is a fully synchronous counter. The other thing, so that differentiates a fully synchronous counter from an asynchronous counter. Now, the other thing that I want to mention is I can see that unlike a natural mod counter now, a non-natural mod counter does not have a 50% duty cycle at all of its counter outputs, at all of its Q outputs. So while I see that Q0 is like sort of 50%-ish, I mean, until we get over here. And, you know, even Q1 kind of, I guess, right? Sort of, but actually, as I would see later on, I don't think it's, no, it's not. So it's again, it's not fully 50%. And same with Q2. And Q3 is really obviously not a 50% duty cycle. So in fact, what I see is the same thing that I saw in a ripple counter. So just like in a ripple counter or an asynchronous counter, the output, the frequency of the most significant bit is equal to the frequency of the clock divided by M, which is the mod number. And again, the mod number is basically, think of it as just how many distinct states my counter has. So in this case, we're doing a mod 9. I have 9 distinct states, which go from 0 to 8 and then back to 0. So that should be your takeaway. And I hope you enjoyed this video. And if you have any comments, let me know.